look like this. It would be a review. It would be a review sheet.
I don't have the packet.
Okay. Chanel, I sent these packets to everyone on Jupiter, I believe. So when you get the chance, have someone go on Jupiter. You can print this out for yourself.
Okay.
Okay. Anyone who does not have the packet, let's go into chat and actually can you chat to me if you do not have the packet? Okay, so we've got one, we know Morris, Chanel, okay, Daniel, Elani. Okay. What I'm gonna do is I am going to share my screen. I have some of the review packet already filled out, but much of it I have a blank copy. So I can show that on the screen share so that we can follow along. Make sure that you have a pencil and a piece of paper. After this, so it's going to be all of your responsibilities to go on to have a parent or have someone go onto Jupiter and get the material and print it out. If you're having trouble with that, get in touch with me because I can find another way to get that to you, if it's by email, whatever is best. But I did create a packet for all of you guys and I sent it to you. So we'll need this for class going forward. First thing that we're going to start with is let's do a quick overview of I'm going to share the screen of what we're going to review. And just so you know, we are not getting tested. There will be no assessment for this unit, but we're still going to review what we learned so that we can retain that knowledge and use it in the future. So I'm sharing my screen. Let's go ahead, share screen. You don't see the screen shared yet, do you? Let's go ahead and try this again. Share screen. Give me a thumbs up if you see the first page of the review packet. Great. So we're going to start this review packet today, and we're going to finish it tomorrow. Our unit is electricity and magnetism. Let's spend the first couple of minutes. I want us to look at these two sections, section 1 and section 2. And on your pieces of paper, I want you to just make a note of which of these things you feel strong in and which of these things you feel like you really need to review more. So for the next minute, just do sections 1 and 2 on your paper. Which sections do you need to review and where do you think you have strengths? And as you're coming up with your areas of strengths and areas where you think you need a bit more review, we can go ahead and chat those to everyone. Let's make sure, Ms. Rahman, I know we spoke about this earlier. Maybe we can enable make sure that the chat is available to everyone.
Okay, I can get that done for us.
Thank you so much. Okay, more chat. Okay, so let's go to everyone. Areas of-
Right, it's enabled.
Great, thank you. Okay, thank you for sharing out Chanel and Carlo. I'm not sure whether that's a strength or an area where you'd like to review. Review, okay. Let's take another minute. I'd like to see some other people sharing out into the chat so that we can get an idea of what we need as a class. Static electricity, everything in current electricity except E. So those are your strengths, Leilani. All right, guys, there are two. Okay, so I guess just to make this easier, let's put just what we need to review. And that's what I think most people are putting. Some of us are putting strengths. Just put what we need to review. Electromagnetism, static electricity. Section 5B, okay, that wasn't part of the instructions, but thank you for looking ahead, Tanzel. We're just looking at sections 1 and 2 right now, but 5B is induction, okay, I'll make a note of that. Series and parallel, All right, let's get started on the first review problems. So I'm gonna actually switch my screen back over. Let's admit Jalen. Share. Screen share. All right. So on your screen, you should see a PowerPoint. The first section here is static electricity. It shows 3 diagrams. Now let's remember that the plus means a positive. This is a positive charge. Here we have a negative charge, and here we have a
Galen, get yourself inside the frame, please.
This is a less positive. It's smaller because there's not as much total charge there. Here we have what's going on there? Here we have a negative charge. So it wants us to draw electric field diagrams. I'll give you the first one as an example because it's been a few weeks. So positive charges, the arrows for electric fields point away. Now remember, this is electric charge. We're not talking about magnetism right now. So electric field lines point away from a positive charge. Go ahead and draw that positive charge with those field lines, and then continue to do the next two images. I'm going to call on scholars to share the field lines that they drew on their pages.
Jalen, remove your hood, please. Yes, you may, Kaylin, quickly.
Mr. Emily?
Yes.
So for the negative one, we put the arrows towards the middle, right?
Yes. Negative charges, the field lines point in towards the negative charge. So
Thank you.
Start to draw this one. For example, we would have, don't do that. We would have, why is it red all of a sudden? We would have negative charge would have arrows pointing in towards it. But you also have to think about what the field lines will look around that positive charge.
Tangent. Tangent.
All right, I'm gonna ask one of you who feels ready to show us the image that you drew on your page for the second one, the positive and the negative charge. I'm getting a feeling that we're still working, so I'm going to give everyone a few more seconds. Let's take 30 more seconds and complete this middle picture. The way that we think that the electric field lines will be pointing, and then we'll share out. It's okay if we don't get it right on the first time. That's why we reviewed. Daniel, thank you for raising your hand. And when we actually share the way that we're thinking about something and we get any misconceptions fixed, that actually helps us learn a lot better. So Daniel, I appreciate your taking the chance there, the academic risk. Daniel, can you show the drawing on the camera? All right, yeah, Daniel. So you've got arrows pointing in towards the negative charge, and you've got arrows pointing away from the positive charge. And I'm going to continue to fill in on the screen here. Interestingly enough, these arrows from the positive charge would actually curve in towards this negative charge, because they're pushing away from the positive here, but they're also being drawn in towards the negative. So we could draw an arrow from positive to negative. On the opposite side, we'd have a positive charge here, would push away in the lower right-hand corner, would push down to the lower right-hand corner. And you'd even get a little bit of a curve to these arrows coming in these directions. So now using that model, go ahead and work on the third image. Now remember that positive has a smaller charge. This positive charge here is smaller than the negative charge, which means that it's weaker. There's going to be less attraction. And the way that we draw that is it should have less arrows. So I'm just making a note for you, less arrows on small. And there should be more arrows on the larger charge. So take another 15 seconds to draw whatever you think the electric field lines would look like. And then I'm going to call on Jason. Okay, Jason, I'm unmuting you. Why don't you give us, show us the image that you drew, and if you want to explain your reasoning, please do that. All pencils should be down. Let's put our eyes on the screen so we could see Jason's work. Kaylin, pencil down.
I just drew positive outwards. I just drew positive outwards and the negative inwards.
All right, and Jason, it looks like you've got, it looks like you have 4. Can you show that again? It looks like you have 4 arrows coming out of the positive. And how many arrows do you have pointing in on the negative charge?
Wait, we're talking about VI?
VI, yep.
Oh, okay. I put 3.
Okay, so let's remind ourselves here that less charge. The way that we show that is we have fewer arrows that come out of it. So you started off by putting 4 arrows coming out of the positive charge. which is a great start. We should curve those arrows in towards the negative charge because negative is going to attract any positive charge. But we also want to make sure that there are more arrows pointing in towards that negative charge because it has a greater charge in general. And the way that we show that is by indicating it with more arrows. So I'm drawing more arrows pointing in towards this negative charge. Give me a hand. Give me a hand if you have a question about the way that we draw arrows. Actually, I'm going to change that. Instead of that, I'm going to ask for someone to volunteer to summarize how we draw electric field diagrams. So how do we draw the arrows for electric fields? What are some of the rules that we followed? Chanel, I'm going to go to you. What's one rule that we follow when we draw electric field diagrams?
One rule we follow is that there's less arrows depending on the size. Like if the positive is small, there's less arrows for that. But if it's bigger, then there's more arrows.
Okay. And in these pictures, what are we actually, we're drawing small and big circles, but what do the small and big circles actually represent?
It represents the amount of electricity coming from the circle.
The amount of electric charge, actually. So that's think about like protons and electrons or a charged sphere. If that sphere has more charge in it, we're representing that by a bigger circle. And if it has less charge in it, we're representing it as a smaller circle. So yes, electric charge. What about the directions? Which direction do we draw arrows? Let's go to Jessica.
We draw the arrows like for positive, it would be coming outward, but for negative, it will be coming inward.
Thank you, Jessica.
You're welcome.
So those are really the two main rules here, that positive charges have arrows pointing away and negative charges have them pointing in. If you have more charge, you have a lot of arrows going in or out of it. But if you have less charge, you have fewer. Maybe you might only draw 2 or 3 arrows coming out of it. Everyone, let's look at question number 2 here. As the distance from a charged particle increases, the strength of the electric field. Look over the multiple choice questions. Take about 20 seconds to pick your choice, and then we're going to share out with our gestures which ones we think it is. Okay, we have about 5 seconds left. So in 5, 4, let's put up our fists. 3, number 1 for A, 2 for B, 3 for C, and 4 for D. Fists up, and I'll count down. In 3, 2, 1, and 0. So the answer is, let's see, we've got 4s, 4s, 4s. Yeah, the answer is, I'm still waiting on a couple, Vicky, waiting on you. Is that Morris? Jalen, I only got the top of your head there, so I can't see your gestures. The answer is 4, which is D. The further away you get, the weaker the electric field is. Okay. This next question, I'm actually going to shift over. Actually, this is fine. We'll use the PowerPoint. So static electricity, this is reviewing the idea that when we rub things together, like when you're rubbing your feet on the carpet, you can build up static charge. You need to use this triboelectric series over here in the lower right-hand corner. And I'm gonna remind you that the types of things on the top, these have a greater affinity for electrons. Greater. And the ones on the bottom have less affinity. Affinity means attraction. So things that are higher up on this list are more likely to take electrons, and things lower are more likely to give them away. So using that reminder, go ahead and fill out. Go ahead and answer these questions 1, 2, and 3. We're gonna take another let's say another 1 minute. If you're already finished, give me a thumbs up if you're already finished. Okay, so we have about 50 seconds left. Things will transfer. I'm also writing on here, why is it making a line like that? Let's not have that happen. Transfer from less to greater. Less to greater. So when you rub two things together, the one that has a greater attraction for electrons is going to grab them. Daniel's ready? Okay, we're taking about another 20 seconds. I think that my judgment of time is a little off. Let's take 10, 9, 8, 7, 6, 5, 3, 2, and I'm going to share. Actually, I'm going to call out on, before I share all the answers, I'm going to call on a couple of you. Bailey, for number 1, electrons. The cotton shirt rubs against a rubber balloon.
Huh? Oh, okay. So I think the electrons transfer from the cotton to the balloon.
Tell me why.
Because since the balloon is rubber, it has like a more affinity for, I think, for collecting electrons or something. And I remember that one time that we were watching I forgot what you call it, but like the demonstration in class, and then the rubber balloon was taking all the electrons. So yeah.
Yeah, rubber has a greater affinity, so they will transfer from the shirt to the balloon. What will happen to the charge of the shirt then, Kaylin? what happens to the total charge of the shirt? It's losing its
it won't
electrons.
be, yeah, so it'll be all positive.
It will become positive. And what will happen to the charge of the balloon? Kaylin, finish it.
Me?
Yep,
It'll be negative.
will become negative. I'm gonna share the rest so that we'll move on to the next series of questions. I'm just gonna share all of the answers on the screen simultaneously right now. Take 10 seconds to make a note of anything you need to change according to the answers that you put. Carla, did you need to make any changes? Good. Okay. So we're going to move on to we're going to skip, if you're actually looking in the packet, we're skipping the next page. So this page that has all this stuff filled out, we're going to skip over this. If you want, like I can make copies of my copy and send them to you. We're going to turn to the page afterwards. That's number 5, and I'm going to switch to my doc cam now so we can work together on the document camera. Okay, give me a thumbs up if you see the doc cam number 5. Is everyone seeing my shared screen? Thank you, Jason. Okay. So on each line, there's a scenario, and we have to decide if it's charging by friction, charging by induction, or charging by conduction. What do we remember before we even start these problems? Let's do a quick things that we remember, and we'll jot these on the papers. What do we remember about charging by friction? I'm looking for hands. What do we remember about charging from friction? Jalen, what do you remember? Jalen, can you hear me? Jalen, can you hear me? Carlo, what do you remember about charging from friction? How do things charge from friction? General ideas.
They charge from friction by getting the electrons like from when they rub from.
Okay. So when you rub things together, electrons transfer. That's the general idea. Let's look at D. I'm not exactly sure how to pronounce this name. I'm going to pronounce it Noir or Nauer. Now rubs animal fur against a rubber balloon. Do we think that this fits into the description of charging by friction, show me on your hands. Give me a thumbs up if this seems to match the description of charging by friction. Daniel, that's not how we use that hand signal.
On task, following along.
Yeah, I mean, he's rubbing animal fur against a rubber balloon, and Bailey reminded us that we did a demo in class where we rubbed a balloon against a sweater, and charge was transferred. So
Yes.
this is an example here of charging by friction. Let's take a look at the next one and see if it matches charging by friction. And if not, we'll think about what we know about charging by induction and charging by conduction. So our shell takes Noah's balloon and puts it nearby, but not touching two connected aluminum soda cans. Then he separates the cans. One can becomes positive and the other is negative. Show me on your hand, give me a thumbs up if you think that this is an example of charging by friction. Okay, give me a thumbs down if you think it is not charging by friction. I only see a few hands, and actually a few videos have cut out. But let's go to Leilani. Why do you think this is not friction? Charging by friction.
I don't think that it's friction because they're not touching.
They're not touching. So which one do you remember? So it's not friction because they're not touching. They're not rubbing against each other. Which ones, everybody think, which do we think that it might be? Could it be induction or conduction? The other two options here are conduction or induction. Tangel's hand is up. Tangel, go ahead, you're unmuted.
Okay, so can you hear me?
Yep.
Okay, so I think that this is induction because it says, because induction by definition is like when you charge an item with another item, but you're not touching, right? And it says it puts it near, Charchel puts it nearby, but it doesn't, but they don't touch, meaning that it can't be conduction or friction. It has to be induction.
Thank you, Tanzel. So induction is when you charge something, you create, you allow charge to move around in the object by never touching it. So we know it's not friction, it's not rubbing, and we know it's not conduction because conduction requires touching. So that's induction. So conduction, I'm writing the note, you should be writing it as well, is charging by touching objects. So once Dauntre touches one of the cans Charchel just charged against the metal rod, both of the objects are then charged. Let's make number 1 charging by friction, number 2 charging by induction, and number 3 charging by conduction. So friction, induction, conduction. Show me in your hands which charging method this is. Is it 1, friction, 2, induction, or 3, conduction? I've got 1, 2 sets of hands. I got 3 hands in the air. Bailey, I don't have a hand from you. Vicky, I don't have a hand from you.
Galen, come on, let's go.
Come like that.
This is an example of charging by conduction because they are touching.
Chanel, sit up, please.
Okay, what I want us all to do now is we're going to skip ahead to current electricity. I'm gonna do one quick example, and then I want you to work on the other example independently. So when current is flowing, we have this situation where a current of 11 amps at 240 volts flows through an electric space heater. We need to calculate the power of the heater. So just like when you're in mathematician's plan, we're looking for the power. The things that we're given are, we know that there are 11 amps. We know that there are 240 volts. And the relationship that we can use, we're trying to find power. We're given amps and volts. Do we have any equation here on our reference sheet that relates these three things? Let's see, voltage, current, and resistance. I have current, but I don't need resistance. What about power? Power, I need to find power. Power is equal to voltage times current. I have both of those things. So I'm going to use P is equal to V times I. And in my solution, I'm going to go ahead and fill those things in. I have P is equal to V times I. So P is equal to 240 volts times 11 amps. 240 volts times 11 amps, and then I get my answer. So I'm going to fill in the answer after that. What I want you to do is take the next, we only have a couple of minutes, take 2 minutes and work on this problem right here. So work on problem B. All of your formulas are right here. I'm going to start to fill in a few of the planning steps. So if any of you need a little bit of a boost, you can look at that. We are given, so it's the same heater. So we know we have 11 amps, 240 volts. And we know that the power is 2,640 watts. We know that it's used for 1 hour. We're looking for energy. We have an equation for energy. Energy equals power times time. Do we have both power and time? Yeah, we have power. This is power. And we have time here. So we have everything we need.
Julie, how do you ask, please?
Okay, we're gonna, let's see, give me a thumbs up if you've come to a solution. Okay, what I'd like you to do for homework is I would like for you to finish this problem. And this is the first thing that we're going to review in class tomorrow as we continue our review of this unit.
You said that's homework, right?
Yes, homework is going to be to finish this problem. And homework is also going to be to print out your science packets. Get in touch with me if you need me to send it to you in an email or some other way. I sent them all in Jupyter as a PDF file. Maybe we don't have access to printers, so I do understand that. I can continue to put these things up on the share them on the screen. But if you have the ability to print your packets, I think it's going to be a lot easier for you.
I don't have the ability.
All right, so that's the end of science for today. And I look forward to seeing you guys tomorrow to finish our review of this unit. Feel free to message me, Jupyter, or email me if you have any questions.